Today, I'm going to talk about Earth's moon, often simply called the moon, but sometimes referred to as Luna to distinguish it from other moons. Before I get into some of the phenomena of the moon, I'm first going to go over some general facts of the moon. And I'm getting all of these from the NASA Planetary Fact Sheet, so you can certainly trust them. As you might be aware, the moon has about 1/6 of Earth's gravity, or, more specifically, an acceleration of 1.62 meters per second squared. This reduced gravity results partially from a reduced mass of the moon, about 7.342 times 10 to the 22nd kilograms, which is about an 80th of Earth's mass. Of course, mass alone doesn't determine gravitational acceleration, seeing as these two numbers don't translate. The other factor determining gravity is the radius, which is an average value of 1,737.1 kilometers, about 3/11ths of Earth's. It is worth noting that the radius actually reduces by a couple kilometers in going from the equator to one of the poles. This actually happens to all planetary bodies and results from the spin of the body. Nevertheless, if you plug in those numbers for mass and radius into Newton's law of universal gravitation, which I won't discuss here, you do get the mentioned acceleration. The average radius gives a lunar volume of 2.196 times 10 to the 10th cubic kilometers, or about a 50th of Earth's. From there, we get an average density for the moon of 3,344 kilograms per cubic meter, about 3/5 of Earth's. Now that we've described some general characteristics of the moon, we're going to move on to its formation. The moon was formed slightly after everything else in our solar system, roughly 4.5 billion years ago. There are some dissenting ideas about how the moon was formed, but by far the best supported hypothesis is that it resulted from a collision with the Earth. Relatively soon after the Earth formed, some other planetoid, about the size of Mars, collided with Earth, kicking up a lot of dust into Earth's orbit. This eventually coalesced into the moon. All the pockmarks on the moon result from impacts with meteoroids. This idea that the moon formed from a part of the Earth is supported by analysis of lunar rocks. It is found that, while depleted of hydrogen minerals, many of them have similar oxygen compositions as Earth rocks. Among the Earth-like rocks are some from meteoroids that collided with the moon. Closely related to moon rocks, we have lunar soil, often called regolith. This is a fine, dust-like powder covering the surface of the moon. Since the moon doesn't really have an atmosphere, this dust couldn't have formed by weathering. Rather, it forms from a combination of meteoroid impacts and solar wind. Solar wind being fast-moving charged particles, like protons, ejected from the sun. Both of these are slow ways to erode rock, but the moon's been there for a while with no atmosphere or volcanic effects to disrupt the process. This regolith is what reflects sunlight back to Earth, making it appear as though the moon were lit up at night. Regolith isn't actually all that reflective, only reflecting about 11% of light incident upon it. The moon is just really bright at night because the sun is really bright. Since we're on the topic of moon reflectivity, it only makes sense to discuss the phases of the moon. It is important to note the sun always lights up some half of the moon. The phases just result from how much of the lit up part we can see. We'll start from a new moon, where the moon appears completely dark. This corresponds to the moon being between the Earth and the sun, and thus not able to reflect any of the sun's light toward us. When the moon starts moving out from in front of the Earth, we have a waxing crescent. When the moon, Earth, and sun form an L, the moon is at its first quarter, with half of the part we can see lit up. This continues on with a waxing gibbous. Once the moon is behind the Earth, the part we can see is completely lit up, giving rise to a full moon. As the moon starts to move out from behind the Earth, we have a waning gibbous. When the moon, Earth, and sun form another L on the other side of the Earth, we have the third quarter. Continuing on, we have the waning crescent, which leads back to a new moon, letting the cycle start again. It is important to note that there is no dark side of the moon. All parts of the moon will be lit up at some point in the moon's orbit. While there is no one dark side of the moon, there is a far side of the moon, where one side of the moon is always facing away from us. This is because the moon's orbit takes roughly the same amount of time as its rotation, a phenomenon known as tidal locking. Before I get too far into this, I should discuss some orbital characteristics of the moon. The moon has both a rotational and an orbital period of about 27.32 days. The moon goes through its orbit at an average velocity of 1.022 kilometers per second. It does, however, take about 29.5 days for the moon to return to the same place in Earth's sky. This means that the phases of the moon cycle through once every 29.5 days. Thus, it is likely the origin of the idea of months. Tidal locking results because the Earth's gravity does not evenly pull on the moon. The parts of the moon closer to the Earth get pulled more strongly than the parts of the moon farther away from the Earth. This causes the moon to form a slight elliptical shape. Nothing noticeable from just looking at it, but it's still there. If the orbital period and rotational period were not synchronized, the moon would start to rotate relative to the Earth, meaning that the ellipse would also adjust in position. Since readjusting orbital and rotational rates is faster than changing the shape of the moon, the Earth then wants to bring the elliptical shape back in line with the gravitational forces. If the moon is rotating faster than it is orbiting, this causes a slowment of the rotation and a speed boost to the orbit, and vice versa if the orbit were faster than the rotation. Either way, the slow processes of lunar deformation is what result in tidal locking. The moon has a similar effect on the Earth. While it doesn't greatly affect our rotation rate, it does still unevenly pull on the Earth. The moon pulls on the oceans closest to it, causing them to rise. The moon then pulls on the whole Earth, slightly less, causing it to move slightly towards the moon, although not as much as the first set of oceans. The oceans on the other side of the Earth aren't pulled as hard as the rest of the Earth, so they appear to also be higher. The sides of the Earth not in line with the moon have their oceans unaffected. This forms the origins of tides. The parts of the Earth in line with the moon have high tides, while the parts perpendicular have low tides. We, as humans, have also been to the moon. There were numerous flybys to the moon, both manned and unmanned, but only the Apollo program made 6 successful landings on the moon. NASA used Saturn V rockets to launch the Apollo capsule to the moon. 12 total astronauts landed and walked on the moon. Neil Armstrong and Buzz Aldrin from Apollo 11, Charles Conrad and Alan Bean from Apollo 12, Alan Shepard and Edgar Mitchell from Apollo 14, David Scott and James Irwin from Apollo 15, John Young and Charles Duke from Apollo 16, and Eugene Cernan and Harrison Schmitt from Apollo 17. In addition, each Apollo mission had one command module pilot who, while they did not land on the moon, did fly the craft to it and picked up their buddies who went to the surface. These command module pilots are Michael Collins from Apollo 11, Richard Gordon from Apollo 12, Stuart Roosa from Apollo 14, Alfred Worden from Apollo 15, Thomas Mattingly from Apollo 16, and Ronald Evans from Apollo 17. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.